Hi everyone, welcome to Past Business Intelligence Virtual Chapter. My name is Julie Cosmano. I am happy to present another or host another Past BI Virtual Chapter session. And we've got a couple of community news, so I'd like to go through that, and then I'll hand over to Rolf Tasma, who's the speaker for the day. All right, I just want to bring to your attention that past elections is coming up, so make sure that you update your past membership profile by June 1st so that you can vote. I think there will be an email sent to you if you are actually eligible to vote for the past election. And if you'd like to volunteer with PASS, please feel free to do so. Go to the My PASS profile, so with your login, and select the My Volunteering section. We do have a number of virtual chapters, so feel free to join any of them and join their sessions too. And we've got a couple of sessions coming up as well from other virtual chapters, so feel free to join them. And if you actually miss some of these older sessions, you might be able to still view the session recordings, just like today's session for BI Virtual Chapter. We are recording this session and it will be uploaded to our YouTube channel, which I will provide more details later in this session. So we do have a couple of SQL Saturday events coming up as well. If you are actually in Australia, New Zealand area, then there's one on June 14th in Christchurch, so be sure that you sign up for that. I think they're combining that with Code Camp as well, so you'll probably get a good value for that SQL Saturday in Christchurch. So Past Business Analytics Conference is actually still running right now, and you can follow the latest news from Twitter. I think the Twitter handle is @PastBAC, if I remember correctly. And yeah, there are lots of exciting news around Power BI for that too. So make sure you stay in touch with Past BA Conference. And Past Summit 2014 is actually coming up very shortly. If I remember correctly, it's about 25 weeks away. It's on November 4th to 7th, 2014. So hopefully, I think I will be attending. So hopefully I'll see you guys around at Past Summit 2014. And if you'd like to stay involved, please visit sqlpass.org. We've got a couple of links here, and our BI Virtual Chapter has got its own website called bi.sqlpass.org. And this is the lovely YouTube channel that we've got. So it's easy to remember, just youtube.com/user/pastbivc. So as you can see, we've got quite a number of sessions being recorded and uploaded there. So make sure that you visit our YouTube channel. Just letting you know, next week we do have another BI session titled Usage of R in SQL Server for Better Data Understanding, and this time it's going to be run at 11 a.m. Pacific time, so LA time. I think it would be very, very early for us here in Australian Eastern Standard Time. Just make sure that you check the time conversion properly. To register, just go to bi.sqlpass.org and you'll be able to see the details about the session as well as the time zone conversion. So without further ado, I'd like to introduce Rolf Tasma, who will be talking about leveraging SQL Spatial Analytics for making business decisions. I met Rolf at SQL Saturday in Melbourne just last month, and I thought his session was wonderful. So I'm very excited to watch this session and having this session recorded. Right, over to you, Rolf. I'll just change the presenter to you. Yes.
Okay, fantastic. All right, I hope that's coming through okay.
Yes, it looks very clear, crisp and clear.
Very clear. All right, fantastic. Thank you everyone for your time and making time. I understand everyone's busy today, but I really appreciate that you can attend this session, and I hope you'll get something out of it as well. I've been working in the SQL Spatial space probably for a couple of years, but in the database space for many years, probably too many years. and this has a very, I have a very keen interest in this topic. So specifically this, I do this session occasionally, and it's typically quite an interactive session, so this is my first time on a webinar, so I hope it comes through okay from your side and you do get value out of it. Before I kick off, the solution, this is not just talking about technology, it's talking about a solution. So this is a real implementation or a number of implementations that we've been involved with or parts of it. So it's not vaporware per se, but it does exist in its component parts in some way through some of our clients. Just to give you some background, I'll give you a scenario that'll hopefully keep that in the back of your mind as we go through today's session and think about the ways that you could apply this type of technology to the sorts of things that you do in your own business. So the scenario is myself and my wife, as an example. My 2-year-old son go shopping on a Saturday morning. We go into the shopping centre. Plans to meet up later on. My wife goes one way. My son and I go another. Off we go. Into the shopping centre, message comes up on my mobile phone. Mr. Tesma, welcome back. Would you like to come up to Country Road to have a look at some shirts for those jeans you bought last week? Well, absolutely. So what we'll do is I'll plot a route using my mobile device from my current location to the Country Roads location, the shop, the element, and plot me a route which is child-friendly or pram-friendly in this case, because I'm pushing a pram with my son in it. Off we go. Following the route, I pass within about 20 or 30 metres of Saba, which is a female clothing store. Message comes up on my phone. Mr. Tesma, don't walk by so quickly. Would you like to come in and get some presents for your wife? It's her birthday next week. Well, absolutely. So in I go, select something nice, scan the QR code that's come up on my mobile device, get a 10% discount offer because I've purchased on the spot, and continue on my route. Go up to the Country Road, buy the shirts, and then go back to my mobile device and then start plotting a new route. Plot me a route from where I'm standing, right outside of Country Road, to where my wife is, and continue to update that route as she moves through the shopping centre to ensure that we meet up at the right spot. Because she's a moving target, she's a crazy shopper. It might sound almost fictitious, but this is in fact how these solutions tend to work. And what we're going to talk about today is the types of ways you could do cool things like we just talked about, and ultimately the technical ramifications of the type of business problems we're trying to solve with this type of technology. That's just an example of a retail sense of this type of application. So as we go through, think about it yourself how you could apply this type of technology. So let's kick into it. Of course, first a little bit about us for people who don't know Dimension Data. We're pretty big. We're about 15,000 people, about 50 countries or so, and we work across pretty much most clients in the sort of the top 100, Fortune 100, and about a $6 billion business or so. But enough about the marketing, let's move on to the agenda. So this is the agenda. We're going to cover off what are these type of solutions. They're called location-based services solutions, or LBS. We'll talk about what the hell these things are. We'll have a look at the technical overview and an architecture of a solution like this. I'll show you how SQL Spatial comes into play with these solutions. So things like the example I gave, proximity, route mapping, these sorts of things, all comes out of SQL Spatial. I'll show you how that works. We can't get past these type of solutions without talking about data. And we're talking about a lot of data. So I'll talk about ways to, first of all, how it's generated and ways to manage it. Reporting and analytics also go hand in hand. So because we're collecting lots of data, we want to see it in aggregated forms in a spatial sense. So I'll show you how we can do that as well. And we'll wrap up at the end with some questions too. Okay. Let's just continue. LBS. What's LBS? Okay, so location-based services are what I like to call value-add suite of mobility services that leverages Wi-Fi infrastructure. So what we're talking about here is mobile devices, such as laptops, phones, tablets, anything that can connect to Wi-Fi infrastructure, i.e. gets a MAC address, has a MAC address, is a target, in quotes, for these type of solutions. And what we're trying to do is provide value to the people on the other end of these devices through that Wi-Fi infrastructure. Typically these solutions are there to track device location, their movements, and potentially browsing activity. So if you're providing Wi-Fi infrastructure, people might want to browse the internet. So you want to capture that location and what they browse, when they browse it, and where they are in real time over a location map such as an airport or a university or a retail shopping centre. More so as well, you want to push interactive services and content back to those devices, such as shopping centre maps, routing information, these sorts of things. Okay, so what can these solutions do? We've already touched on a retail solution, but let's talk about a little bit more detail here. They're really mostly about capturing traffic behaviours and patterns. Primarily you want to try and do one of two things, or both things potentially: optimise a network infrastructure or monetize foot traffic that's already happening. So an example might be, if you're a university, you might want to look at ways to optimise student movements, but you're not really trying to make money out of that. But if you're in a retail sense, people are moving through your shopping centre anyway, so you're looking for ways to monetize that traffic or provide value to those devices and the people that they couldn't get otherwise, and try and increase the number of people who come to your stores. So an example might be capturing this sort of data gives you the ability to position store locations in the most optimal position, such as you can say, based on the foot traffic that goes through my shopping centre at certain times of day, a Hudson's coffee store will be best located here as opposed to on level 1, and here's the reasons why, because I know exactly who moves by there, when they move by, their profile and these sorts of things. So you can start to value and position stores, and also price it for your for the people who actually spend time in these stores as well more accurately. You might want to do something like a pop-up store. You can say between 3 p.m. and 5 p.m. on Monday to Friday, this particular area of my shopping centre is going to be best suited to a Maybelline pop-up store. And the reason that's the case is right around the corner is a high school, and a lot of the girls walk through here at this particular time. Put a pop-up store here. Other times of the day, forget about it, because the demographic's not there. So it gives you the ability to create a monetization opportunity that previously you didn't know about. Other things you might do is out of bounds. So an example might be at an airport, I want you to track and report an alert to me when a device, any sort of mobile device, moves in and out of security repeatedly but never actually gets on a plane. And when that happens, I want you to notify the security guard closest to that device and actually tell them to have a look at what's going on. So pretty cool stuff. Another kind of, I think, a nice benefit is to do things like tracking medical equipment with RFID tags. High-risk patients, as an example. We did an implementation in a hospital where we tracked, I think it was dementia patients, so to actually find out where they are in the hospital at any one particular point in time. So quite clever. You could also do things like tagging high-value casino chips. So an example is, as a casino operator, I'd certainly want to know when, say, $10,000 and higher value chips enter my casino, and certainly when they leave, and more so when someone goes to the cashier and puts $1 million of $10,000 chips on the counter. I want to scan those with an RFID tag scanner and know which are counterfeit and which are real. So this is the type of solution that could pay for itself very, very quickly. So they're just some ideas. And by the way, every time I do this session, someone comes up with a new idea that we just hadn't thought of. So it's quite a growing area. It's quite a new area. Other things we can do, provide consumer experiences, such as, I walked by Saba within 20 or 30 metres in the example I gave at the start, and I received a message stating, it was effectively a marketing message, stating for me to come in and have a look at some clothing items for a birthday, as an example. Another pretty cool example is, you might want to do something like set up media stations all throughout your shopping centre. And so just great big TV screens, in other words. But because they're Wi-Fi enabled and also all physically wired, you could do something like, when 3 or 4 teenage girls stand within 5 metres of that particular big TV screen and they dwell there for 10 seconds or more, I want you to flash up a Maybelline ad that is loud enough so that those girls hear it. And when they do, I want you to track what happens next. So very, very, quite simple to do as well. We're just talking about data here. Last point, consumer services, and I've touched on some of these as well. Pretty simple things like, where is it? So where is the store in relation to where I am? Take me to, or where am I? I'm lost. Where's my car, as an example, in the car park? So pretty cool stuff. Hope everyone's still with me. So what type of data is captured by these solutions? So not surprisingly, the primary key is the MAC address. Every single Wi-Fi enabled device has a unique code. It's the MAC address. So not surprisingly, we use this as the key to pretty much everything that happens in the solution. Interestingly enough, if you didn't know, the MAC address, I think it's the first 6 characters, can be dissected to identify the device manufacturer, such as Apple or Nokia. And I'll show you an example of this. So MAC address is the key. There's some things that we can collect, such as movement-related dimensions and measures, such as date and time, not surprisingly, map location, X, Y, Z, within a certain defined mapping, a Wi-Fi enabled mapping area, dwell time, so how long a device, a MAC address, has spent in a certain location, such as an X and Y, when it moves from that location, what is its direction of travel, what is its speed of travel, and how far did it travel. So, and I'll show you examples of all of this. If the Wi-Fi, the movement analytics solution, collects, well, I guess if it's actually got people on the other end of the solution. So if we're tracking, casino chips, they're not going to browse the internet or register. However, if it's a shopping center example, you will certainly have a registration capability. So you'll have a dimension and some attributes around that as well. Things like the basics of name, date of birth, gender, those sorts of things, they're pretty basic. So nice to have are things like occupation, education and income, or associates such as myself and my wife, we have associated devices as an example. The reason is you can start to build up some pretty powerful and very interesting demographics about the types of people who use your solution and ultimately make better decisions around what to do with your networked environment, such as the shopping center and those sorts of things. The better demographics you have, marketers love this, the better your outcomes will be, not surprisingly. Now, of course, we can also do aggregations. So think about all the data we're collecting. So every time a movement occurs, we collect that data. Looking at individual points is interesting. Looking at aggregated points is very interesting. So what we can start to do is do things like what's called device crowding. So in a particular, say, hour of day, how many devices on average or max or min happen to aggregate or group together in a certain area? How long have they spent there cumulatively? From a certain area of my, say, shopping center, what is the most common travel paths for a certain person moving in a certain way? So we can basically say of a certain demographic, if they're standing in this area of the shopping center, which way are they much more likely to travel, such as a likely travel path or a common travel path? We can also do frequency. How often does the same device turn up all the time, such as the airport example? So all the sorts of things you can do. Now this does sound like the future, but it's wrong. This is today. So when I did the session in SQL Saturday, I came down from Sydney the day before, and I thought just for the hell of it, I'm going to check the T's and C's on the Qantas free Wi-Fi over in Sydney. I hope this comes up okay on your side. Long short though, may collect or track certain information, etc., usage patterns, travel patterns, website page views, traffic patterns, and record your MAC address. Okay. So this is today. This is not tomorrow. This is happening right now. So if you're in Sydney, actually I haven't checked Melbourne. I'm from Melbourne. If you've ever connected to the Qantas free Wi-Fi, you have been giving up this information already. Okay, so this is not tomorrow. This is today. Just keep that in mind as well. Let's break down the solution and see what it looks like. So there's lots of different ways these type of solutions can be put together. The ones that we've worked on to date have been based on Cisco, but there's other solutions too. There's some Bluetooth solutions out there. There's some Apple solutions that use things like a thing called iBeacons. So I'd encourage you to do your research. If you're interested in this, do your research and see what you think is the best fit to your customer or your environment as well. We happen to use Cisco quite a bit. So I'll talk about the solutions that would tend to use in the past. So for these type of solutions, you need Wi-Fi infrastructure. In other words, you need to get someone, a whole host of people actually, to physically go into the environment and wire up what you want to network. So if it's a sporting oval, you need to get people out there and actually physically put in access points. We've used Cisco historically. For the solutions that we've put in, the crux of the whole solution, the engine that does the calculation, the triangulation of position, is Mobility Service Appliance, or the MSE. The MSE gets the data from the access points. I'll show you an architecture diagram in a second. and effectively triangulates the position of that device, and it can do 50,000 a second. If you exceed 50,000 a second, that's fine. You just add another one and it scales linearly. Off it goes. If your solution browses the internet, you need some sort of proxy. I would recommend it anyway. We use Blue Code to make sure the data going out is clean and neat. If the solution has people, you also need a registration appliance. We looked at a number of appliances. We ended up building a web service for it as well, in this particular case, in a POC sense. So that's what you need out of the box. Out of the box is quite expensive, as you can imagine. If you're doing lots and lots of access points in a very big area, we're talking about a lot of cable and a lot of access points. So the higher the density of the access points, by the way, the greater the accuracy of the positioning. So some of the solutions we've put in have an accuracy of 10 meters, depending upon the broad spectrum of the access points. Some have an accuracy of about 3 meters of some of the things that we've scoped. It can depend. More accurate means more access points, more cost. Let's keep that in mind as well. So the custom developed components are the parts that we're kind of interested in here. So it's a data acquisition. So we've got to get data out of these appliances, such as the MSC, the Mobility Services Appliance, the Blue Code appliance, registration appliance. We've got to get data from these things. We do it via ETL or ELT, whichever your preference is. Because they're appliances, they don't talk SQL per se. They have to talk .NET. They're APIs. And so we have to call APIs to get the data out. We have a data warehouse layer, SQL 2012 or 2014, either or. Analytics and reporting layer as well, it sits on top of the warehouse. On top of that as well, we have a device layer. So an example might be if you have a solution that is using that has people, and those people do things like browse the internet, look for routes within a shopping center, those sorts of things. You'll need something that presents that to the end user. That might be an app, or it could be something like a HTML5 service, which is what we ended up using as well. Let's have a look at how this might look from a macro perspective. So what we have here is a whole stack of devices within a Wi-Fi enabled area. The positioning of those devices is being continuously picked up by a number of access points. That data is sent off through networking switches, routers, controllers. Simplified this to one tiny little icon because it is fairly complex. We'll just say it goes through it. What happens here is the movement tracking information is sent to the MSC. The MSC does its magic and triangulates the position of those devices in relation to what the access points say, where they say they are. If it's browsing the internet, outbound traffic is routed locally out through a Blue Code proxy out to the internet. And if it's a registration that someone's registering for the first time, that will go through to a registration appliance or service. What happens though, we've got to get data out. We call APIs to do that. We do it via ETL. That's actually, by the way, a series of .NET applications which are running on a cluster, some of these solutions that we've scoped. Long short though, it'll find its way into a data warehouse through a staging and into a data warehouse for analysis purposes. I'll show you some demonstrations of that. At the start of the session, I gave you an example of me, say, walking within 20 or 30 meters of the Saba store and receiving a marketing message. That comes out of the warehouse. So an example might be you might set up things, what we call triggers, not triggers in the database sense, but triggers in the sense of this solution. And one of those triggers might be, I am Saba. I will create a rule that says if a male walks within 30 meters radius of 30 meters of my store and he meets this criteria, such as being married and his wife has a birthday within 2 weeks, when that criteria is met for that movement, I want you to send a marketing message off to a content service and send that down to the person. And it does that through the warehouse as well. Let's have a look at the type of data that we collect, so the actual tables themselves. Now this is a simplified view. There's quite a few tables, but at the end of the day, it's actually a fairly simple architecture, a fairly simple table schema. Let's break it down. In the middle, we have a thing called shopper, dim shopper, dimensional shopper. It has a shopper key, which I'll talk about, and a MAC address, name, mobile contacts, those sorts of things. The dim shopper table will have a row for every single registered shopper or network user, including anonymous. I haven't talked about this to this point in time. So an example might be when I walk with my device into a Wi-Fi enabled area and my Wi-Fi is turned on, I will be picked up, I will certainly be identified and then picked up via the access points, even if I haven't registered. The reason that's the case is the Wi-Fi access points can detect that your Wi-Fi is on and start to get details about that device, even if you haven't registered with that SSID. That is from a database sense, that is an anonymous user. When that happens, you will be created as a row inside DIM Shopper. You'll have your MAC address, but nothing else. We won't have name, mobile, those sorts of things. We just have the details of the fact that a device has turned up for the very first time. It has this MAC address, and it was in this location. So we do actually track that. I'll tell you why we track that in a minute or two as well. Fact movement. This is probably one of the more important tables. This is what we call the hot table or the hot row. For every single device within a Wi-Fi enabled area, this table will show its current location. It has a single row per device, its current location that is on the network right now, including anonymous. So an example might be, say when I walked, my example at the start of the kickoff of the session, when I walked into the shopping centre, it would say that Rolf Tesma, he has his phone on, it has his MAC address. At this particular date and time, I was in this map hierarchy location, this XYZ, the physical map hierarchy, apologies. I had this device, I was in this XY location, and I stood there, I dwelled there for, say, 15 seconds. And that's what's in the fact movement row. When I start to move, when I start to physically move around the shopping centre, every time I do a move, the previous row of where I was will be stored in a history table. My current role will be updated with where I am right now. I hope that sort of makes sense. So what will actually happen is as you move through a Wi-Fi enabled area, fact movement is where you are at that instant in time as you're detected by the access points, and the history will be where you were leading up to that point of where you are. So what you can actually see here is every time you move, in most of the cases it could be 3 meters or 10 meters depending on the accuracy of the access points. Every time you move through this Wi-Fi enabled area, you can start to build up a lot of data in the fact movement history table. If you take an example is if the detection area is 3 meters, if you move 300 meters, you will have created 100 history rows. Every time you move 3 meters, it creates 1 history row. You move 300 meters, it's 100. You move 3,000 meters, it's 1,000. So over time, the history table can get actually very, 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 very big. Because we're not talking about one device, we could be talking about 100,000 devices moving. And any particular second that they'd be moving or standing still, these tables can get very, very big. What about if you're browsing the internet? So for solutions that do allow internet browsing, in most of the cases we've looked at in the past, this tends to be an anonymous. Anonymous is not allowed. So if, for example, the shopper walks into the shopping centre, starts moving around and then opens the browser and starts browsing, a row can be created for each browsing URL. So an example is I might stand outside of Sabre in my example at the start of the session. I receive the discount voucher, but instead of actually going into Sabre, I might say, I think I can get a better deal than this, and I hit the web to search around for Sabre's competitors. I will start to create fact browsing rows. And it's going to say, the shopper key is me. I was in this particular map hierarchy location within the store. It might be, say, 20 meters from Sabre. And at this particular date and time, I browse these URLs. And I can actually start to build up a profile about what I'm doing and when. Keep in mind the triggers we talked about earlier. Triggers can be defined on almost anything. In a solution like this, they can be complex to implement, but you can actually do it like that. You can say, when a certain person browses a URL, and that URL has this string in it, I want you to do something else. So you can start to build up some pretty cool things in here. So keep that table structure in your mind, because we're going to talk about this when we start talking about the actual solution and the spatial demos. Data. So how are we going to manage some of these big tables? So here's an example of the data warehouse of how it could reside. So what we have is the fact movement table. So keep in mind that this is probably the hottest and most important table in the solution. So when we first started talking about these type of solutions and POC'd some of them, we started looking at SQL 2012. So SQL 2014 is out now, of course. Things will be different, and I've sort of pointed out where it kind of might change. So what we have is our fact movement table. If there's 100,000 devices on the network, this table will have 100,000 rows only. Because its need for speed is very, very high, a lot of the solutions we've sort of talked about in the past would put this on SSD. So this is today's data only. This is not an exact sort of solution for this, but it's approximately how it looks in the sort of the POCs. So this is the fact movement data. If we're using SQL 2014, the fact movement table wouldn't be sitting on SSD. It'd probably be sitting in Hackathon for performance reasons. Pretty small table. It's an instant in time. If you lost it, it's not a big deal, but it needs very, very high performance, obviously. On the other side of this, though, is the not so small table is the fact movement history. So the way that we sort of have architected these solutions historically is for every single day we create a new partition. And so the real time is in fact movement. The historical is in our fact movement history, partitioned by day. So at say 12:01, just past midnight, we would bundle up all the changes for the day and throw it in the empty partition and create a new partition. Because we're creating a partition by day, and SQL 2012 has a limit of 15,000 partitions, that's about 41 years. So it's a lot. So we don't think we have to worry about that. Well, certainly I wouldn't in my career anyway. So what happens after... got to cover this off first. So what we would do is, because the data actually doesn't change, we can set any historical partitions to read-only and put a column store index on it as well for performance reasons. If you're using SQL 2014, you could use updatable column stores. You probably wouldn't need to, though. Main reason is that data doesn't change. So if you're standing in a certain location and you move 3 meters in one way, and then you turn around and you move 3 meters back to your original position, that doesn't... You can't undo your movement. That's not an undo of movement. That's just a new movement. You've actually created 2 history rows. You've got to go back and forth continuously. You're not changing anything. You're creating new data. So this is why, from a history perspective, data never ever changes. From the instant it's created, it never changes because you can't go back in time. That's very, very important. Empty partition on the far right. So what we have here is high velocity data comes in throughout the day, stored in the fact movement table, and a variety of things happen. So I mentioned this is a slightly simplified diagram just for the sake of it. But at 12:01, midnight, the fact movement table is bundled together, thrown into the empty partition, set to read only, and then the backup of the database only backs up the new partition. Why? Because why back up everything else? It hasn't changed. So what you can do is you can back up the full database, say, on day number 1, and then every single day for 365 days, just back up the new partition, and on the first day of year number 2, you might back up the full database again for recovery's sake, to make it a little bit simpler to deal with. So that's how you can actually manage these very, very large tables. So fact movement history, browsing will probably be in the same boat. Let's look at some spatial functions.
Sorry, Ralph. While we're having a bit of a pause there, there is a question here. In terms of privacy issues, is there any, or are there any privacy issues with tracking anonymous devices?
Yeah, that's a very good point. Yes, I can best answer that by saying it's still being tested in court. There was a case a little while ago. I'll answer that with a scenario, with an example and a scenario as well. About 6 months ago, over in London, I think it was in Fleet Street in London, a very smart entrepreneurial person, I don't know exactly who it was, had set up effectively what they call smart rubbish bins. They're very sort of funky looking rubbish bins with media screens on them. But they were also Wi-Fi enabled. And what they did was, when people moved up and down the street, it started to build up profiles and returning frequency of those MAC addresses. And I also knew where they went. So if, for example, I walked down the street and I continue into to McDonald's, and then it recognises my MAC address, the 55th time coming back, and it goes, flashes up a Hungry Jack's ad for Hungry Jack's across the road, that in many ways is actually almost identifiable. So it's building up a profile and tracking information. There was a big uproar about that, and although it didn't violate any rules because it couldn't physically attach that MAC address to me, in theory that's allowed. But because it was such a big uproar about being tracked anonymously, even though, in other words, they weren't made aware they were being tracked, it was such an uproar, the solution actually got physically removed from their environment. So long short, it is not illegal to track someone anonymously as long as you do not collect any identifiable information that ties them to that MAC address unless they specifically agree and sign off for you to do that. So I hope that answers the question. Long short though, I think it will continue to be tested as time goes on.
Very interesting.
I hope that's answered the question. So I'll give you a scenario for this as well. If this is rolled out to, say, Maya, where Maya owns the point of sale, the POS systems, and I anonymously walk in, I never register, but my MAC address anonymously walks in. They know that my MAC address is at a POS station where I hand over my credit card and I pay for the Country Road shirt I talked about at the start of the session. That technically is illegal because it knows that my card paid for an item and it knows that my MAC address was standing at the POS. So in theory, because Maya owns the POS and owns the data of the movement data, it knows that that was me. And in theory, that's actually illegal unless I signed it off. So it depends is the answer I have to say when it comes to IT. Watch this space, I think. Yeah. I hope that answers the question, but we'll move on.
Interesting insight. Thank you.
Let's look at some SQL Spatial functions. And that's all right. If any other questions come up like that, do feel free to fire away. It is a little bit controversial, this area, and still being tested. Let's look at some SQL Spatial functions around ways to track movements and how this is actually done. So, excuse me. So to track data, to track device movements, we need 2 points, not surprisingly. So where I was, or where I am in fact movement, and where I was last in fact movement history. So pretty easy to do that, of course. The points should be related. They should be my points, not say my location and someone else's location, such as Julie's location. It doesn't make sense. We'd have to do the same points. So to do distance, you can do this with a function called stDistance on the geometry data type. So note we're not using geography for these. So geography is on a global scale, circular, so it takes into account movements around the globe. We're looking at a flat plane, in our solutions anyway. So we use geometry. Now you could do this with stDistance, or you could do it mathematically with good old Pythagoras as well. So this is going to be a blast from the past to mathematics in high school in many ways. There's Pythagoras' theorem. I'll show you an example of this in a second. Easy to do speed. Now there's no geometry functions to do this. It has to be done mathematically. Pretty simple. Speed is distance over time. I'll show an example. Direction. Again, no geometry functions. Has to be done mathematically with some tan functions actually. Like I say, it's a trip back to high school mathematics. So I'll show an example. Let's go ahead and do this. So first of all, I want to kind of acclimatize you with what we're looking at here. So I hope that everyone can see on their screen now my excuse me, my management studio. I'm going to connect to my sample database. The first thing we want to do is I want to show you how we convert MAC addresses to integers in the system. So keep in mind that because the MAC is the key, but the MAC is a string, it's inherently not very nice to use in a data warehouse just for performance reasons and storage. So we convert it to an integer and do this with the function. So here's an example. So this is I have a Nokia phone and standard issue, and this is my MAC address. So we'll just convert that over. So I've got a function that does that, converts from MAC to int, and then I get the integer and I convert it back as well to actually show that it works. And again, a little function here that says, given a MAC address, what's the vendor? So we can actually go ahead and do this. So I hope that you can see that okay. That's the integer which comes back. That's the character version of my MAC that I passed in originally, and it knows that it's Nokia in this case. So we actually can start to use some of this information to dissect what's happening, and then also use it for keys as well. Let's go back the other way. This is let's have a look at an Apple device. It's an integer version, that's the char version, and it knows it's Apple. So not really rocket science, but it's kind of nice to have, and the functions are easy for performance reasons in the warehouse. All right, let's have a look at some shoppers. So this is the dim shopper table I showed you earlier. So this is me. That's my shopper key and my MAC address. So Rolf Tesma, mail, etc., my date of birth, location, I have a Nokia device, etc., my phone number. Here's an example of an anonymous person. So we know that it's a shopper key because it's a conversion of the MAC address, but we know nothing else except for the fact they have an Apple device. But we know when they were first created. So in this particular case, this anonymous shopper turned up for the very first time in my Wi-Fi enabled area on this particular date. I wouldn't really say shopper. We're talking about devices. Okay, so this Wi-Fi device turned up in my shopping center at a certain time. Let's have a look at some movement rows now. So I'll just have a look at my two tables. I have my fact movement table, which is a row per device, currently in its current location, and the history table at where the devices have been. So it's empty at the moment. I have a stored proc to insert data. It's called movement insert. So what we do is we give it the date and time that we moved, the MAC address of the shopper, or the MAC address of the device. For the MSC needs this, but it's the access point that last detected my, or that I'm associated with, that's last detected my movement. For the sake of the demo, let's just use a dummy. The X and Y location of that MAC address, so the access points tell me this, or the MSC. For the simplicity, I'm taking out the hierarchy. So this is a hierarchy of where I am within the mapping location. So in this particular case, it might be something like I'm in a certain building on a certain floor in a certain precinct, as an example, which I'll talk about and show you examples of. But for simplicity, we're cutting that out. I'm not debugging. So let's go ahead and do that. Okay, so what we're looking at here is the date and time that my movement occurred in this particular case, integer form. I collect these things called path and path step. So what we do is every time a device is detected, I assign it a path and a path step ID. And as you continue to be associated with the network and move throughout the center, I keep the same path ID but increment the step. And so I can easily join together like paths within a center. If you go outside of the network and then walk back in, say into the car park and back, and you drop off the network, you get a new path ID when you walk back in. Your step will start at 1. Here's the shopper key. I'm not using the hierarchy, so these are all zeroed out, but that would be a key to a table where the dimensions are, which I'll show you in a second as well. Here's my map XY location, 12 and 15. I've got a dwell time here. So from the system's perspective, it only really knows that I was detected at a certain date and time by a certain access point, and it knows that I was in that location for, as far as it's concerned, 0 seconds I've been there for. Now that will change when I start to add new data. Let's go ahead and do that. Same MAC address, I'm moving from 12.15 to 14.9, and actually let's go ahead and do that. Okay, so what's happened here? My original movement row has moved down to movement history, which is this table. Same details as before, saying that I was in location 12 and 15 at a certain date and time, and I was there for 84 seconds. So in other words, that discussion we just had took us 84 seconds, because from the system's perspective, that's how long it thinks that I was there before I actually moved. So that's the time between the executions. Now when I did move to my current location of 14.9, I departed at 0.05 meters a second at an angle of 153 degrees off the center, which I'll show you an example of, and I walked 4.47 meters at that particular point in time. And this is my current location, 14.9. Let's quickly add a few more rows to see actually what happens here as well. So I've added a whole stack of new rows. Now, you notice that I actually executed them all at once. So from the system's perspective, it thinks that I dwelled in these locations 0 seconds. I should have put a wait for in between them. But this just shows an example of the types of movements we can do and the path step as they increment and then move through the center. So you can see quite quickly how data can get pretty big pretty quickly. Simply by moving 100 meters, I might create 30 or 40 rows as an example. Now you add that, multiply that by 100,000 people, and it starts to get very, very big. And that's just one day or one instant in time. Okay, so we'll talk about volumes in a little bit of time as well. Calculating distance. Pretty simple. We have a current x and y and a new x and y. We can do it mathematically via good old Pythagoras, which is this square root function here. Or we can do it geometrically as well using a function called st distance. let's look at the ST distance, because this is probably the more interesting one. So what we do is, excuse me, we create a geometry from point and a to point using these X and Y locations. And what we do is we say, my from point is a geometry data type. I'm going to create it from a text, which is just points X and Y. And my to point will be geometry from text, point X, Y. Long short though, what we're doing is calling the function called ST distance on my from point and passing it my to point. What this is basically saying is, using from point, get the distance to to point. And then I'm doing it the other way around as well to prove to you and show you that it actually works either way. So let's go ahead and do that. So pretty quick. So this is the Pythagoras' theorem one. So 4.4721, etc., etc., etc. So happily, thankfully, it's exactly the same answer that we get from ST distance. So this is the ST distance function. From and to has this value, and this is to and from. So they're all exactly the same. As a matter of fact, under the hood, I wouldn't be surprised if ST distance function, geometry function, does exactly what Pythagoras' theorem does. I'm not sure for real, that's probably what it does. I'll hold off on the visually and spatially bit till the next section, I think, to make a little bit more sense. Let's have a look at speed. You can only do this mathematically. So we have a time to traverse a certain distance and how far we travel. This is actually from an earlier calculation, 4.47 meters. We'll go ahead and do this mathematically. No spatial functions here. Pretty straightforward, traveling at 1.49 meters a second. So pretty simple. Direction is not as simple. So what we need is an X and Y. We need a previous location and say a current location, so moving from and to. And what I've done is created a little function to do it. So you pass it the values and it will return to you what the positioning is. Let's go ahead and do that. Okay, so what that's saying is taking the angle between those 2 points is 153 degrees off north. So in other words, vertically going straight up, if you go round the clock, it will be 153 degrees off that north value. So in other words, moving from point A to point B, travelled 4.47 meters at a certain speed, and I travelled on a direction of 153 degrees off my initial point. Now the reason you think direction might be important or may not be important is it's actually quite interesting to collect, because then you can start to say, as people are positioned or located in my shopping centre, I can actually say for any particular location what is the most likely or common direction that people will travel, and when they do travel, how far do they go and where do they go. So that's quite interesting. So you can build up a very interesting dynamic visual map about directions within your centre, and then you can start to optimize your centre based on directions. Pretty interesting stuff. So we haven't really seen much in the way of visualizations here. We just looked at mostly sort of spatial and mathematical functions. Let's make it a little bit more interesting. Let's talk about proximity. So to work with proximity, you need at least one data point, such as where I am right now, such as a fact movement or movement history. So you can do it with not only where you are, but where you were. But typically you need something to search against, such as a list of stores or other devices, such as give me the proximity of me to Country Road or me to another device. So this starts to get quite interesting. Now you can also say things like draw a radius to show what is within my area of vision or within a certain distance. So you can do this via the geometry function called STBuffer and STContains or STIntersects, and I'll show you exactly what these are and what they do. I'm sure you could do this mathematically. I don't know why you'd bother. The functions work beautifully, and I'll show you an example of this. Other cool things you can do is nearest and furthest elements. Okay, so this is as a direction and a distance as opposed to a route, which I'll talk about in a second as well. So there is a big difference. So we'll show you how this works with the ST distance function, and you can do it mathematically, but again, I don't know why you'd bother with that. So let's look at proximity. Now this will start to get a little bit more visual as we sort of go through, and I'll demonstrate this to you. Before I do that, let's have a look at my fictitious shopping centre. So I have a couple of dimensions. I have a map centre. So in other words, that will be the shopping centre. I have floors within that centre, such as floor 1, 2, 3. We have precincts on floors. So that will be things like shopping centre zone, food court zone, walkway zone. Then we have elements such as JB Hi-Fi, Hudson's Coffee, things like that. So let's have a look at what they look like. So here's my first kind of fictitious centre. It's the Bondi Junction Shopping Centre in Sydney. It's only got one floor, and it's got a number of precincts. So we have some walkways, a retail shopping area, food court, etc., etc., as examples. And it's got a whole stack of elements as well, such as JB Hi-Fi, car park, Target, walkway areas as well. And it's also got these things called, and I'll show you, and just keep in mind this is fictitious, so things called walkway cells. So in other words, between elements, to say we've got a shopping centre with stores laid out, the actual walkway that sits between elements such as JB Hi-Fi and other things, that's divided up into small 1 by 1 metre segments called walkway cells. And that actually helps us position and find out where people are in regards to 1 by 1 metre squares. And I'll show you an example of this. Let's see what this looks like visually. Now I'll bring you through this a little bit slowly because it's pretty important we grasp this part. So what I've got is I've just selected from a view, and that view just pulls together those 4 tables into a kind of a common view. So here's an example of the very first row, and I'll show you what the geocode looks like. This is JB Hi-Fi. It's a retail store in the technology zone, and it's a type of retail stores. It's on ground floor of Bondi Junction. What does this look like? So if you weren't aware, within Management Studio we have a thing called spatial results. Now what this is actually doing, it's plotting this geo. A geo is a geometry data type. It's plotting and showing it to you visually. I'm going to talk through this just to make sure we understand it. So this is my shopping centre, my fictitious shopping centre map. So over here we have Target, we have a car park, which is this sort of purple region. We have JB Hi-Fi, Coles, etc. And as we zoom in, we can start to see the other stores coming up. So these kind of multicoloured cells here, they're my walkway cells, okay? They're 1 metre by 1 metre segments of the actual walkway carved up into little pieces. We're doing this for accuracy and reporting purposes, which I'll show you some demonstrations of. So when you start to zoom in, and let's have a look at, say, the distance between Target and JB Hi-Fi. I go right in close. I can see that 1, 2, 3, 4, 5, there's about 5 walkway cells, in quotes, between those 2 stores, or about 5 metres. We can tell for real using functions in a minute. So I hope that sort of come through okay on your side, but we'll be seeing this map a lot as we go through the demonstrations. What stores are in my radius? Let's have a look at this. So what we do is we have an X and Y and a location. So what we're going to do is my location is going to be based on the position of 4021, and I'm going to create a point of that. And let's actually see what this looks like. But before I do that, actually, I'm also going to create a buffer. So using my location, I want to create a buffer of a distance of radius. The radius is 15 metres. So in other words, get my location and draw a radius of 15 metres around it just to see what this looks like. Let's go ahead and do that. So there we go. You may not see it. It's a very, very small point right in the middle. That's my location of 40 there and 21. That's a 15 metre radius around that point. Not that interesting until we start to do things like overlay. So what we're doing now is I'm just going to say, give me everything from the map that we saw earlier. Based upon my location and a radius of 15 metres, I want you to give me everything on the map that is contained within that radius. So ST contains the geometry from the map, and it's physically contained in that radius. Let's go ahead and do that. So that's my initial radius, and here's my new radius. So here we go. That's my location. I know that I'm now, based upon using the radius function, within that 15 metre radius is the Phones R Us store, and I'm physically standing in that store, and right next door is Saba. And these are all the walkway cells surrounding the store itself. But you can sort of see there's a couple of gaps in here. So I've got some big gap up here, but we don't know what it is, and the main reason that polygon or that element or store doesn't fit in my radius. In other words, it extends past it. I've got a gap on the bottom as well. So what we want to do for completeness sake, we need to see what else is in there. And we do that via a different function. This time, instead of using contains, we're going to use intersect. So in other words, give me the same function, give me the same query, but show me anything that actually touches that radius. Let's go ahead and do that. So we've seen our radius. We know what it contains, and here this is much more interesting. This is actually what it touches. There we go. So there's my location. I know that I'm in Phones R Us. Saba's right next door. Jetty Surfer's down the south. Pumpkin Patch. There's a walkway here and a walkway here. A whole stack of cells. Crazy John's, etc., etc. This actually becomes a lot more interesting to look at, and also from a mapping perspective as well, makes a lot more sense. So you can start to see how these functions can start to play and kind of help us out making decisions. Let's look at distance. Same x and y, going to create a point. What we're going to do now is we're going to see what the actual distance is between all of the locations on my map and where I'm physically located. I'm going to plot that out. So here we go. Actually, I'll expand that right out. So my location is on the top of the list. So not surprisingly, it's zero distance between me and where I am. But the closest store to me from a raw distance of 0 is Phones R Us. Now the main reason, I'm inside that location. I'm physically in that store. Saba has a distance of 1.29 meters. Let's not be tricked by this. It might sound, yeah, that's actually very, very close, but until you spatially see it, it doesn't make a lot of sense. I'll show you why in a second. Another tricky one's the car park at 28 meters, and I'll show you why this also doesn't make sense. But from a direct line perspective, this is actually correct and valid. In this particular case, we're using st distance as the function. Let's see what this looks like visually. Okay, so zoom right in here. So that circle is me. I'm inside Phones R Us with a raw distance of 0. So Saba, it's saying, is 1.29 meters, but in reality, that's just that tiny little gap between my circle and Saba. Really, from a routing perspective, I might have to travel more like 20 meters to get inside Saba. But from the distance function, it actually doesn't know that. It just knows how close something is from a line perspective. So it can't actually work that out. You can sort of start to see how all the other stores are close as well. Now I mentioned as well the car park. It's saying the car park's 28 meters. But in reality, to walk to the car park, we have to go down a corridor and a right around. So what it's detecting is the closest point to that car park. I've also got a line that will show me that. So smack in the middle of that is me. So it knows that Telstra shop is in this direction at a certain distance. It believes the car park is in this direction at a certain distance. And you can start to see visually how the st distance function works as well, and how it actually sort of starts to plug together distances. It has no idea of routing, it knows distance only. So that kind of makes sense and where the risk might be involved to use that function. Let's plot out a couple of paths. So I have a little stored procedure where you give it a shopper key and you say how many steps you want to include. Let's actually see what this looks like. So in this particular case, shopper, I think it was 260. Yep, so shopper 260 had presented themselves 3 times in my shopping centre. In this first path, they presented themselves at this particular point in time. They moved 10 times and they dwelled for 105 seconds. 3rd of the 8th, 2011, they moved 4 times for 16 seconds and so on and so forth. This is what it actually looks like. So now I can actually see this particular path is where they actually went. But again, in the context of what? So what we have to do is add in maps. Let's go ahead and do that. I have a little error here. There we go. Now this is going to be a lot more interesting. Okay, now this is much more interesting. Now I can actually see where they moved in relation to other stores. Now if I wanted to, for each point where direction changes, I could use the st distance function to see what is the closest element to where that person was at any particular point in time, or how long did they dwell there, those sorts of things. You can start to see how visually data makes a lot more sense, in a spatial sense anyway. Okay, moving on. Aggregations. Now this is also pretty interesting. The functions to date have all been talking about individual points or 2 points. let's look at lots of points working together, either in the fact movement or the history table. But again, you need something to reference, such as stores or other devices. So to calculate something that's called dwell time, now this is a very simple SQL function, average, max and min, standard deviation, but you need to visualize this over a map for it to make sense, and I'll show you an example of this. You can also do things like crowding indexes, such as how many people are in a certain area at any particular point in time, using things like count and distinct count. Again, you need to visualize that. Let's see the demo. So just connecting to my database. I have a little CTE here. So the first thing we're going to do is we're going to get the top 10 hot locations. So what does hot mean? What I'm doing is I'm going through my map, and I'm going through all the fact movements, and I'm joining that with my center map on the element keys. In this particular case, I'm just summing up the values of things, movements, close to those elements, and I'm ordering it by a count of movement rows. So in other words, show me which areas of my store had the most movements. We'll go ahead and do that. Okay, so the top one is this guy here. So walkway cell 1394, doesn't mean a lot to me, had a total of 38,000 movements and a cumulative dwell time of 490,000 seconds. Okay, doesn't make a lot of sense. We have to see what this looks like. Let's go ahead and do that. So now I'm going to join with my CTE. I'm going to throw in the map to see what that actually looks like as well, or the actual elements themselves. So now I've got the same report, but I'm going to show you what that looks like. Again, not that useful, but let's actually just zoom in on here, count of movement rows. Okay, so here are the cells, and we know that they're walkway cells, and here's the one that had the most movements, 38,492, this particular cell, and I can see that there seems to be a bit of a pattern emerging here as well. But again, it doesn't mean a lot unless you see it in the context of something else, such as a map. Let's expand on this query and bring in all the map elements. Okay, now this is starting to make a bit more sense to me, and something potentially I might even use from a reporting perspective as well. So let's zoom in here again. So now I can see, I think this was my hottest cell, that's it, 38,492 count of movements. And now I can see that that cell was close to Phones R Us, it was close to Hudson's Coffee, Crazy John's Telstra, etc. So again, looking at data as a table kind of means something, but looking at it spatially, you might actually start to make much better business decisions around this. Maybe this is an area for optimization. Maybe that corridor's too small. We're getting too many people crowding through. To improve flow and throughput, we might need to change something. So you can start to use spatial visualizations to help make a business decision around the way and the structure of your environment. Right, the last function, routing. So you remember the example I gave with Saba. I was in Phones R Us, but Saba is 1.29 meters away. To know for real how far the two stores are away, we have to use a routing algorithm. The one that's been around for a while is called A*. There's variations of A*, but A* is kind of the big one that most people would use, or variations of it. Now, it's not new. It's been around since about 1968. It's actually a graph traversal algorithm. It's not really much to do with spatial data, but it's a way to plot routes between traversable points. It will find a least cost path from one node to another node, and it will always follow the least expected total cost or distance as well. That's pretty cool. It does take into account distance already traveled, and it's a complete algorithm. So in other words, if a solution exists, it will find it. Some other algorithms will stop short when the cost of trying to work out the path gets too high. A* doesn't work that way. It will simply say, I'm going to find it if it exists. The demo I'll show you is a .NET application that leverages this algorithm. You can get the algorithm off the web. There's pseudocode and those sorts of things. I recreated this algorithm in T-SQL, but because of the nature of the way the algorithm works, it's quite a costly algorithm, so it can take a very long time, and T-SQL is not a particularly good place to do it. So .NET was much better. So I hope that comes up on your side okay, but what we're looking at here is a little Pathfinder .NET application with our map that we all know and love by this stage, I'm hoping. And it's pretty simple. What we're going to do is we're going to say, let me take a path from Phones R Us to Saba and find that path. So there it goes. So there's a little path that traverses through, not exactly perfect. The algorithm's not perfect in this case. It actually shows the path that we would take to go from Phones R Us to Saba. So it's not 1.29 metres. It's actually a much, much greater distance. And we can continue to do things like show me the distance from, say, from JB Hi-Fi through to building maintenance, and there's the route. Or show it to me from Toys R Us to Coles, as an example. And there it is there. So the A-star algorithm itself, and this is a very fast implementation, is quite clever. It identifies, it knows cost, it knows the map, it knows when you can or can't walk through certain walls. You can also start to attach value to squares to say certain types of areas are actually more difficult to traverse, or you can't traverse if you're in a pram, as an example, or a wheelchair-friendly route. So A-star can help work out this, or its variations can work this out. So it's quite clever. So keep in mind, ST distance, good for single directions, A-star needed for routing. Okay, let's talk about some data. I know that we're probably getting close on time, but we need to sort of talk about a little bit about data, and I'll go through this a little bit quickly. Let's talk about a scenario. So the large shopping centre retailer, so it's open 9 hours a day, 7 days a week, has about 68,000 shoppers going through at a peak hour and peak day. So it's very busy, okay, very, very busy. We have to make some assumptions. Let's assume that 3 hours a day is peak and 6 hours a day is off peak, so about 33% of the load. Let's also assume that 40% of the shoppers have a trackable device, i.e. they have a phone, or a mobile phone or a device, and the Wi-Fi is enabled. So in other words, we can track them. History tells me that's a bit low. It's probably more like 60%, but for the sake of it, let's go with 40. Let's assume that people who are registered browse 10 URLs an hour, and every year we have about a 5% growth rate. So more people start to consume the service. So what happens? On year number 1, we have about 39 billion rows, movement rows, or about 1.54 terabytes of data. Now, the movement rows are actually very, very, very small. They're about 50 or 60 bytes, including compression. So 1.54 terabytes, that's not that scary. I mean, most of us have probably seen or even using systems that are doing this today, and it's not that scary. Okay, so what if the requirement is to retain data for 7 years? In most cases, the retention period's forever. Let's work on 7 years. 289 billion rows, or 11.39 terabytes. Starts to get a bit hairy for a single store. So the reason is, once you get over a couple of terabytes, you have to start thinking about things a little bit differently. How do you do backups? How do you do restores? I've got a dev copy. I need another 12 terabytes. I've got a test copy, another 12 terabytes. So it starts to get very, very big quite quickly. But in reality, in 7 years' time, who cares? I mean, everything's going to be in the cloud, right, surely? Or it's going to be on an SSD. And so it doesn't really matter what the storage is. We'll work it out when we get there. Businesses like to expand, and this one's going to be no exception. Including the one big shopping centre, they open up 8 more across the country. They also want data to be retained for 7 years. 2.6 trillion rows, or 103 terabytes. Okay, so it's starting to get a little bit hairy. So the reason, we may need to consider some very specialised SQL solutions to manage the data. Everyone's heard of big data. And it wouldn't be a topic about data if we didn't talk about it as well. I'm a little bit sick of hearing it. But let's talk about the accepted marketing definition. So the marketing definition of big data kind of has 3 things. Some of them have 5. We'll just talk about 3. They call it the 3 Vs. So velocity. Yes, we do have a velocity problem. Using a scenario of 9 stores, we're talking about 245,000 rows a second coming into that movement table and being spun off to the movement history table. So it's pretty big. 100 terabytes of data, to me that's big. Okay, so that's something we have to be concerned about. And also we have, potentially, do we have a variety problem? No, we don't, because what actually happens here is the data is very well structured and defined, and it's a very, very tight schema. We've seen the schema. There's no, in quotes, big data concerns here, per se. So we don't really have a big data problem in the traditional marketing sense. But we do have a data problem. We've got to manage this. SQL can do it, not surprisingly. So on day 1, We could look at something like an SMP solution, effectively standard server solution, something like a Cisco UCS and backing onto some sort of SAN storage such as EMC or HP, doesn't really matter what it is. The scale of these type of solutions, get up to 100 terabytes without probably losing sleep. Just simply the nature of the way that data is read and written. Okay, so you could probably get by with this pretty easily. But think about all the assumptions we just made. We don't really know how these solutions work until the solutions are in. So we have to think about day N. So day N may come at day number 2, it may come at day 365, it may never come. Okay, but we need to have a consideration or a solution for it. We can consider something like APS, which is the Analytics Platform System, or used to be called PDW, it's now called APS. MPP, Massive Parallel Processing Compute Solution, up to 64 nodes. So in other words, a whole stack of SMP boxes working in unison to get throughput, mostly for reads, for reporting purposes. Scale up to 6 petabytes. I don't know, many people are using 6 petabytes at the moment. And I think I would never sleep if I had a 6 petabyte system. But nevertheless, it could do it. Reporting and analytics. Last section before we wrap up. Now I want to show you some examples of the type of reporting and analytics we can get out of these type of solutions. Let's break across the reporting services, and I'll show you, I'll start there as well. So this is a little reporting services portal with a whole sort of stack of reports on here that we've created for sample purposes. So the first one I want to show you is what's called device contextualization. Now what the hell are we talking about here? Think about movements and browsing history. They're not really related outside of the shopper that's doing it. So a shopper is in a certain location, or a device is in a certain location when they browse the internet. But that's not really related except by time and the shopper. So this report helps us identify that. Let's have a look at the structure of this report. So we have a whole stack of parameters. We can say, show me this report by certain map elements, such as show me people who browse things outside of JB Hi-Fi, as an example. A from and to date, so only between a certain range or a certain hour of day. Or people that browsed on a certain device. Maybe you're a male or female or single or married, as an example, or an age range. Or show it to me only via host URL, so people who browsed dimensiondata.com, as an example. And also have this thing called map element range of 5 meters as default. So in other words, show me stores within a 5 meter radius. I won't run the report, it's run already. Excuse me. I want to draw your attention to this sample. These aren't real people, by the way. These are just fictitious people out of AdventureWorks. Okay, so our friend Kitty, I know that Kitty is a female of age 50 to 59, and on a certain date and time, she browsed this URL. Okay, now in the context of where she was at that particular point in time, we get where the movements were before she browsed, and what happened when she browsed, and what happens after she browses. So what we have here is the date and time of where she was as she moved through the center. At a particular point in time, she was near building maintenance, then she was near Coles at a certain distance. She dwelled outside these locations for a couple of seconds, and then where it's blue, from this point on, is when she clicked the go button on her browser. So right at this particular point in time, she was just outside building maintenance, 0.76 meters. She dwelled there for 73 seconds. What was she doing? Well, she was probably looking at the weather feed, considering, will I actually go shopping in Coles or go outside? Who knows what she was doing. And then she went on, after that 73 seconds, and walked by Phones R Us, walked by Coles, again by Phones R Us, and back again. So you can start to contextualize what happens in the environment. But again, because this is spatial, we need to see it. So let's go ahead and do that. So we're going to drill into that particular shopper's location and where she was and what she was doing. Let's let that report run. You always wait longer when you're always waiting for something to go. Okay. What I'm going to do is zoom in on Phones R Us down here. If anyone's tried to use spatial reporting within reporting services, you'll know there's some limitations. Unfortunately, you don't get the same panning and zoom features that you get in Management Studio. They just don't exist in reporting services. That's a bugbear of mine, certainly when doing projects like this. All right, so this is up. So it's a very cut-down segment of the same report that I showed you earlier. What we're actually looking here is the function of st-intersects of a certain location. In this case, it's Phones R Us. So it's the st-intersects of all the stores in that location. And here's the path. The green dots indicate where the shopper stopped at a certain point in time, or she dwelled. In this case, she dwelled in this location for 4 seconds. And then this location for 4 seconds, and on she goes. The blue path is the actual traversing path. So that particular shopper, her first movement, the total dwell time and total movements of 22. The red dot indicates how long she spent there. In this case, this is it. This is the 73 seconds where she stood in the context of the environment when she hit the browse button. And this was it right here. So we know that she was close to building maintenance, and then she went on to continue her movement. Or was she drunk or something? Who knows? But she was all over the place, put it that way. And then we have some other paths on this side. You can see the arrows right over here. I hope that's relatively clear. That's the direction of movement. So we know that she moved through the shopping centre in this way. So pretty interesting. So looking at a table is one thing. Looking at it visually, completely different. So quite interesting stuff. The other report I want to show you is this one here. This is what's showing the device average dwell time by map element. So what we're seeing here is the actual map element, such as the stores in my shopping centre, the hours of the day, and the colour of the cell indicates how long on average people dwelled there. So phones are us, people dwell the longest, the 159 seconds. It's pretty hot, and then down it goes. The green indicates the areas which they haven't dwelled much at all. So what we can do here is let's look at, say, phones are us. So about 8 a.m. we had the longest dwell time just outside phones are us. Let's have a look at what happened there. So we can drill into this report. And this is where the 1 metre by 1 metre cells breakdown that I talked about earlier come into play. Okay, so here's phones are us. What we have is all the 1 metre by 1 metre cells, and the colour of the cell indicates the average dwell time. So the red cells, people dwell there longer, and the green cells, people dwell there less. So you can now start to visualise within I think this is a 5 metre radius outside phones are us, how long this dwell time is. And you can actually increase this as well to get a little bit more of a different view on that. So it's pretty cool. So again, seeing tables of data is one thing. Seeing visualizations is a completely different case. And here's a 15 metre radius outside phones are us of all the different cells. So cells where there's no colour is actually doesn't meet our criteria. So pretty cool stuff. The last thing I want to show you from a reporting perspective before we wrap up is Power View. So Power View, if you haven't seen it before, is pretty cool. I like it a lot. I think it's still got a little way to go from its maturity perspective, but tell you what, I'm certainly glad it's here. This particular report is showing us a visualization of this particular case. It's the colours are the age brackets, so the age brackets of my consumers or my shopping centre users. The cumulative dwell time across the bottom of this chart. So in other words, the further along this chart they are, the more time they spend in my store. Okay, they're the people you want to target. You want people who spend there the longest. You want to try and monetize that traffic. The vertical axis is how much money they have. So the higher up this chart they are, the more money they have and the longer they dwell. Now, we have an IT system that's telling us if you're female 30 to 39, you dwell the longest and you also have the most income. And what we can start to do is see what this looks like over any particular month of the year and see how they compare to other segments of my market. And this is just using aggregations within our database, okay? This is actually coming off a tabular model, of course, because that's how Power View works. And we can start to see where how different times of the year change, okay? The size of the circle is also the shopper count. So you can see in December, we had about 39,000 shoppers. And in June, we had 77,000 shoppers. So not only are there more shoppers in June, but they also dwell longer. Okay, so that's actually really important. You might change the way that you structure your marketing campaigns or your shopping centre to target that. What we've done is I've looked at every single element. What about just JB Hi-Fi? So if I'm just JB Hi-Fi, what does this look like just for me? So this is people within a 5 metre range of JB Hi-Fi. Well, females in that age bracket are still the top of the market. And we have other elements as well. And we can continue to select our stores to see which ones are the busiest stores based on my demographic. So that's pretty funky. What about locality? Because Power View is very, very good at maps. So what we're showing here is every single registered person has given us quite nicely, given us their postcode. And what we're plotting here is the postcode of the people that came to my shopping centre, and that was in Bondi, and I'm not from Sydney, so I don't know exactly where Bondi is. It's a fictitious store, of course. And what we're seeing here is the segment breakdown of ages, different colours of different ages, and the postcode region. We can start to see what's happening there. And again, what we're showing here is how many people came through on any particular time of year, and a bit of a breakdown of whether they're female, male, married or single. So again, if I was, say, JB Hi-Fi, I might say, show me where people came from all around Sydney to come to my Bondi store and actually walk by within a 5-metre radius of JB Hi-Fi. So this is actually now targeting very, very closely specific stores. Now this might be quite interesting because JB Hi-Fi might say, well, that's pretty interesting date information. I've got a huge segment of population coming in from the west. I might open up a couple of stores of JB Hi-Fi in the west there to target that market. And you also can see here the times of year where most people come through. So it's quite interesting to sort of see and see how that breakdown works. You might say, let's actually look at certain segments of the population as well. So pretty funky. But like I said before, I didn't really need an expensive IT solution to tell me that men, in this particular case, make up the lowest shopper count and actually dwell the least amount of time. I'm not a particularly big person on shopping centres. I think I fit that criteria. Okay. Contextualization and browser movements. All right, so questions really. So we've finished the session. Oh, this is something you might be wanting to try yourself. I've left a little link at the bottom there. If you're interested in SQL Spatial, one of the best blogs I think going around, although he's moved on to AI now, is Alistair. So this is a link that I saw on his site, and it's a very clever little, kind of fun as well, little patchwork animal you can create right within Management Studio. Really cool stuff. So I encourage you to have a look at that. It's a really cool site. But I'm happy to take questions. I'm not sure if any have come through since we started. But feel free to sort of ask questions now or between now and when you think of them. My email address is on the start of the session. Feel free to flick me an email. I'm more than happy to answer those.
Thank you so much, Rolf. We are actually over time, but I thought I'll just let you go on because the session is being recorded anyway, so all good. Let's see, we do just have one question here. No, actually, someone just left a note, thank you. So I think we're all good. So thanks once again, everyone, for attending this session, and thank you, Rolf, so much for presenting. And I think it's a really good topic, especially around, tracking and all that stuff, even though it's a bit of a controversial topic in a way, but from technological point of view, it's definitely here, and we just have to make use of the existing technology and come up with something creative. So as I've mentioned before earlier, that this session is being recorded and is available from YouTube, and it's so hopefully you'll enjoy this session. And I'd like to thank Pragmatic Works for sponsoring this session, and I will draw a random prize for one of the attendees, and I'll send the details to you on how to claim the prize. So I hope everyone have a good day, and I'll see you next time.